Okay, question number 2. Welcome to One Concept Per Day portal. And this is my second question for this today. And the first question we have seen about how the magnetic forces acts when we have two parallel wires and how to calculate the magnetic force. Okay, and then if you have two parallel wires and so on. Now let us apply the same thing. Okay, over here. And so this question is taken from 2005 May paper. And let us start with this. So on the diagram shown below, draw the magnetic field pattern around a long current carrying conductor. We have a long current carrying conductor. And what's the direction? Direction is going upwards over here. Current is going upwards. Draw the magnetic field lines. So 3 marks. So we know you can find out the magnetic field lines by wrapping this pen around like this, which means it goes in a circular path like this, right? So therefore you will get concentric circles like this over here. Concentric circle like this. At least write 3 circles, 3 to 4 circles. Second circle here, third circle over here, third circle over here. Okay, now what does this tell you? Now it's for 3 marks. 3 marks you will get 3 circles. No, it's not like that. Okay, the first thing that you have to specify what is the direction of the circle. The field lines are directed like this. If you specify it in the wrong direction, you won't get mark. First thing. And secondly, these are all concentric circles. Okay, some students what they do is they write one circle here, other circle here, and so on. That is incorrect. Okay, so first one goes for concentric circles. Concentric circles. The second one, concentric circles. Second one goes for direction. Proper direction you have to mention. And the third one is the distance between the circles increases. See, here it is smaller, then here it is bit larger. If you want, I can put one more circle also here. I can put one more circle also here, like this. Okay, so distance will increase. That means what? When you move away from the current carrying conductor, the magnetic field starts reducing, right? In the previous problem, I already told you about how does the magnetic field depend upon the current carrying conductor and the distance, which is said to be V is equal to mu naught I divided by 2 pi r. This formula is not there in your textbook. Okay, and they will not also ask you about this. I am just giving you an information regarding this. Where r is nothing but the radius of the circle and I is nothing but the current carrying conductor's current. If the current increases, magnetic field increases. If the current decreases, magnetic field decreases. Similarly, if the radius increases, magnetic field will reduce, and if the radius decreases, the magnetic field will increase. That means closer you are to the conductor, the magnetic field is higher. Farther you are from the conductor, the magnetic field is lower. Okay, now let us move on to the next question. The diagram shows a coil consisting of 2 loops of wire. The coil is vertically suspended. Okay, so you see there are 2 loops of this wire, and then the distance between them, what is this? This is your diameter. Let me write diameter over here. Then the pitch, what you call it as, is 0.2 centimeter. Each loop has a diameter of 6 centimeter and the separation of the loops is 2.2 centimeter. The coil forms part of an electrical circuit, so the current may be passed through the coil. Okay, you are passing an electric current. What does it mean? When an electric current passes like this, what will happen? The current will now go like this, round, 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 and goes away like this, right? So which means when the current is going like this, its current is going like this, then what is the magnetic field? When the current is going like this over here. So how is it going? It is going like this over here, and the magnetic field is like this over here. It's like this over here, right? See, it comes up like this and it goes like this, turns upwards and goes upwards, right? So it goes like this and then goes upwards, spirally upwards. So therefore, the magnetic field, my thumb represents the magnetic field, it's downwards. Okay, now state and explain why the current is switched on in the coil, the distance between the 2 loops changes. Now what happens is, now the current goes like this. Let us say I am applying the current here. Okay, if it is very difficult to visualize, I can do it in the opposite side also. Okay, let us first do this one. Current goes like this, it goes like this, then you see it comes like this, then it goes like this, then it goes in this direction, and once again at the top loop it goes in this way, and then it goes in this way. So this is how it goes. Okay, so as a result of this, when the current, let us look at only the topmost coil, topmost loop over here. Okay, let me call this loop A, let me call this loop B. Okay, when I look at the loop A, the current is going in this direction, and then the magnetic field is directed downwards, right? Let me write it down here. when the current is going like this, the magnetic field is directed downwards. Which is the north pole? This is the north pole, and anything that is directed upwards, what I will do is I will put two arrows over here. Okay, this is not a convention, I am doing it for myself to explain it clearly. So I will say this is your south pole. Okay, so remember, south pole is not represented like this. Okay, so I am just doing it for my own convention. I am showing it like this over here. Okay, so this is my north pole. For the first ring I have shown, for the first ring A I have shown, for the second ring which is being present over here. Okay, so here also the current is going in the same direction. As a result of it, north pole is directed downwards and south pole is directed upwards. Now I hope you got the answer right. What happens? When north pole, this acts like a magnet, this also acts like a magnet. So we have one north pole here and you have south pole over here. What will happen? These two will come closer to each other, right? They come closer to each other. So thus you see there will be an attraction. So now let us write down what is that we have. This is for 3 marks. State and explain why the current is switched on, the distance between the loop changes. So what is that you need to write? This for 3 marks. First one is, you should say that the current carrying conductors or the current carrying loops acts like a magnet with opposite poles directed or facing each other, right? That's what happens. See, I can show you here. So this is what happens. North and south pole are facing each other. Okay, then second point. After this, what happens? Unlike poles. Unlike poles. What is unlike poles over here? North pole and south pole. South pole attract. Attract. Then third point. Therefore, distance between the loops decreases, and this will be less than 0.2 centimeter. How do I know that? Because it's already given here, right? This is initially when the current was not flowing, this was a distance. When the current is flowing, this gets compressed like this. Okay, this comes downwards, this also goes upwards. So this is 0.2 centimeter. See, you can also consider it like this. You can say the same thing happened even in case of your current carrying conductors, straight current carrying conductors, right? In straight current carrying conductors, what happened? There was a force of attraction. So here also you see, this is carrying a current in this direction, this is carrying a current in this direction. So both of them are carrying like this. So this appears to be parallel over here. This is exactly parallel, but only thing is it is curved over here. So it is curved like this and goes like that, right? So as a result of this, there will be a force of attraction. Because of this force of attraction, the distance between the two loops will become shorter. Okay, now let us move on to the next one. When there is a current I in the coil, a mass of 0.1 gram is hung from the free end of the coil, returns the separation of the loops to the original value of 0.2 centimeter. Okay, once again, a little bit out of portion, but still this question can be asked by giving the relevant information. Now let us understand this. You have the coil like this, and this is like this. It's given over here. It's given like this over here. Two coils are given here, and then this is being connected here. You add a weight over here. Now, because you passed a current initially, this coil came closer to each other. This coil came closer to each other. The moment, because it's going closer to each other, you feel, array, there's a possibility that these two can touch each other. As a result of it, there could be a short circuit. So what I want to do is I want to prevent this. So to prevent this, what I do is I add a weight here. When I add a weight, what will happen? The coils which were like this will now start expanding like this, right? Will now start expanding like this. So now, as a result of it, the coil now becomes, as usual, this much big over here. See, earlier this was the case without a mass. Without a mass, when there was a current, passing like this, when there was a current passing like this was the new distance d dash. Now, because of this, what you do is you added a mass, okay, and the current is still passing over here. Current is still passing over here. As a result of it, what happens? The distance now increases over here. Distance now increases. Okay. Now, what is being asked? So, when there is a mass of 0.1 gram, mass of 0.1 gram is added over here from the end of the free coil, returns the separation of the loops of the two returns to the original value of 0.2. So, once again, it comes to 0.2 centimeter. Earlier, it was 0.1 centimeter. The circumference C of a circle is given by C equal to 2 pi r. Okay, C equal to 2 pi r. We know this. Calculate the current I in the coil you may assume that each loop behaves as a long current carrying conductor. Okay, see, this loop, this turn will be parallel to this turn, okay, because the current is going like this. So let me write it down. So when I want to write like this, what I can do is I can now write this turn is like this. Okay, this turn, let me call this turn as A, let me call this turn as B. Okay, so now I have written turn B, and now I am going to write turn A also. Turn A over here, and you see the currents are moving in the same direction like this over here. The distance between them is seen to be T is equal to 0.2 centimeter. Now what can happen? So we already seen when you have two conductors which are parallel to each other and each of them is carrying a current I. Let us say this is carrying a current I and this is also carrying a current I. The first thing is we can find out what is the magnetic field due to this conductor, due to conductor B at conductor A. So what will be here? This conductor A. So this is conductor B. So magnetic field here would be equal to B is equal to mu naught I divided by 2 pi d. Where what is d here? D is the distance between the two wires. Here what is the d? D is 0.02 centimeter. Okay, now I will use the same logic over here, and then I'll get this particular expression. I'm not substituting anything, I'm just keeping it like this over here. Okay, and then now if this is the magnetic field over here, it is equal to saying that a current carrying conductor is present in an external magnetic field. So therefore, the force acting on A is equal to I multiplied by the magnetic field multiplied by the length of the wire. This is what we have. Now, what is I here? I do not know. I need to find out here. This is a question. I multiplied by, what's the value of mu naught I by 2 pi d? Let me just substitute. Mu naught into I divided by 2 pi d. Okay. And what is the value of L? So here he has given you a loop. You may assume that each loop behaves as a long straight current carrying wire. Which means what? You have one turn like this, okay, and you have another turn which has been stacking on top of it. So the current is now moving like this. This current is moving like this, and as it goes over here, current goes like this over here. And the radius of this coil is R. The radius of this coil is R, and you say treat this as it behaves as a long straight current carrying wire. What should I do? I will unfold this and I will consider this to be a long straight current carrying conductor. That's what it tells you. So similar to this one, I can also unfold this and put it like this over here. If that is the case, what is the length of this conductor? See, if this radius is R and this runs for one full circle and then it goes upwards. Okay, and as a result of it, this will be equal to 2 pi r. 2 pi r would be the circumference which I have unfolded over here. So thus I can now write this as 2 pi r. Now I have written all the values. Now what I need to do is substitute everything. So now I will write, and this Fa. Now what's happening over here? See, because of this one, these two wires will come closer. Now, since it comes closer, what do? You apply an external force over here, a weight here, so that you pull this one once again apart. So initially, it is like this, okay, because you pass an electric current, it moved nearby. Now what do? You try to apply a force over here and you still bring it backward down to the same position. That's what has been happening, which means the applied force over here should now be equal to mg, right? It should be equal to mg. Now what I will do is I will substitute all the values over here. I will write mg is equal to mu naught, let me take up the values, mu naught into I square. Now there's a 2 pi here, there's a 2 pi here, goes away here, and then what is that you left out? This is R is here, and this is D is here. Now what is the value of R? Let us write down each and every value. This you can get it from your data booklet. Mu naught is nothing but 4 pi into 10 to the power of minus 7. I square, I'll write I square as it, I do not know. What is R here? If you go back, so what is the R here? R is nothing but the radius of the coil. See, diameter of the coil is 6 centimeter, radius should be 3 centimeter. So I will write this as 3 centimeter. Okay, before that, where is it? Okay, so I have this as into multiplied by 3 centimeter. 3 centimeter, I'll write as 3 into 10 power minus 2 divided by D. What is the value of D? What is D here? Distance between the two coils. What is the distance between the two coils? This is 0.2 centimeter. Okay, so therefore this is 0.2 centimeter. 0.2 into 10 to the power of minus 2. So 10 power minus 2, 10 power minus 2 goes away. Now let us do the calculations of only the rest of the parts. Okay, so therefore, let me keep it over here. Okay, so this should now be 4 into 3.14 multiplied by 3 is equal to so much. is equal to how much? 4 into 3.14 into 3. Then this divided by 0.2. When I do this, I get 188.4. 188.4 multiplied by, here you have 10 power minus 7. 10 power minus 7 into I square. Now what is there here? Mass. What is the mass I am adding? 0.1 gram. 0.1 into 10 to the power of minus 3. For grams I am converting into kg, multiplied by g. Multiplied by g. 10 over here. So now what I can do is, I can now say this and this goes away. I have 10 power minus 3 here. So I square will now be equal to 10 power minus 3 divided by 188.4 multiplied by 10 power minus 7. When I do this, what do I get? 10 power minus 3 into 10 power minus 7 becomes, this goes upwards, becomes 10 power plus 4. 10 power plus 4 divided by 188.4. Okay, let us simplify this also. So this, what I'll do is, let me take up my calculator. Okay, so this should be 1 divided by 188.4. I get this value, multiply this by 1, 2, 3, 4, 10,000. I get this answer 53.07. 53.07. What do I need? I need I. The value of I would be square root of 53.07. 07. Now let me take the square root of this also. If I take the square root of this, I get this 7.28. This should be 7.3 amperes. That's the current which passes through the wire. In order to make it come nearby, okay, by 0.1 centimeter is going to be so much. So as a result of it, when you apply a gram of weight of 0.1 gram, definitely it will restore back to its original. Okay. Thank you.